Let me start this thing. I think it's plugged in already. Power is on. I've got it backwards. Let me turn it on. Has anybody figured out this one yet?
Is it, as you spin it, do you use like a, you touch something to it, and then use it, and like the little ridges vibrate?
Okay. I should just leave it at that. It makes a pleasant enough sound. Controls them over.
It's like these other times. Yeah.
I'm a sucker for sentimental songs. Okay. You thought I wouldn't be so cruel. Just one verse maybe? No. Okay. So here we have this thing that's rotating. I don't know how well you can see, and maybe in the course of this thing you may end up looking closer. But this thing, this is a series of discs you can see that are up against each other on a spindle, and on the discs are these rubber things which I cut from rubber matting, and they've got ridges on them about every eighth of an inch. So one of the things that always surprises people is that the smallest one makes the lowest note. So I've got this deal here where I'm using this as a plectrum. The styrofoam cup is acting as a sound bowl. I mean, it's just something to radiate sound into the air. You need a good surface area to move a lot of air. So we've got the plectrum in the cup, and it's dragging over the ridges at some number of ridges per second. About what that waveform must be like. The waveform is a very rough approximation of whatever this thing's doing as it dances over the ridges. But it's doing it at some reasonable frequency in the hearing range, And the small one is producing the lowest note. Why?
Slower radial velocity.
Okay. The slower radial velocity is a nice way to put it. Basically, this thing only has, I don't know what, 50 ridges or something, and this one has 200 ridges or something, and they're both doing the same number of rotations per second. So we're getting a lower frequency. There's basically less ridges going by per second on the small one than on the big one. There's a whole history to this. Before we had oscilloscopes and frequency counters and a lot of really cool computer stuff that can help students visualize this. The idea that frequency corresponds to pitch was a difficult idea to demonstrate, if you think about this. And so there was a kind of a cottage industry of physics professors inventing ways of doing these demonstrations, and you can find some of these old physics texts that have woodcuts of these beautiful, elaborate devices that were used for classroom demonstrations. And one of them was that we used to come up sometimes with something called Savart's wheel, or sometimes called Savart's disc, which was basically this, a single disc of this. And you'd have these ridges going by, some number of ridges per second, and you'd have the something you drag against it, and you'd have a counter telling you how many rotations, and you'd know how many ridges there were on the whole thing. So you'd get some number of, you'd be able to do the multiplication and see that A above middle C was so many bumps per second on Savart's wheel. So this is what this is. This is actually a great demonstration in the classroom because it's so awful that the kids, get a big kick out of it.